Hi, everyone. Welcome to this recording in which we are going to tackle the mathematics Olympiad problems which were set in 2023 for the junior round 3. You know, the juniors write 3 rounds and the final round is round 3. So we are going to look at the solutions to that particular competition, South African Mathematics Olympiad competition, which is organized by the South African Mathematics Foundation. We have already done one recording for 2024. It will be on YouTube somewhere. And today we are going to look at the 2023 problems. So without much further ado, let's go straight to the first problem, question 1. Okay, in this problem here, it is said that the list of integers 3, 4, PQ, 14 has been arranged in ascending order. Okay, which means that each one of these is smaller than the next one, and no numbers equal. So just bear that in mind, no two of these numbers are the same. And the question is, how many pairs are there so that the average of these 5 integers is also an integer? So the issue is about finding the average of these 5 numbers. So let's just calculate the average. The average is the sum of these 5 numbers. 3 plus 4 plus 7, 7 plus 14 is 21. 21 plus the 2 unknown numbers divided by 5. And you want this to be an integer. So to be an integer, it means that the numerator must be a multiple of 5. Right? So you got 21 here already. So the sum of these two could be 4 to make it a multiple of 5. Or it could be 25 is the closest multiple of 5. 30, which means that P plus Q is 9. And if you check this out, you'll see that what we are doing is we keep adding 5 to this, and these P plus Q, if P plus Q is any one of these, then it will definitely make this an integer. All right, so that is a condition on P plus Q. But remember, P and Q are integers, whole numbers, and they are between 4 and 14. So I think we just bear that in mind. They're all strictly less than, because they said that no two numbers of these are equal. So you're looking for 2 numbers between 4 and 14, which will add up to this. Obviously, no 2 numbers between 4 and 14 will add up to that. But for 9, if you, the closest you can get is 4 plus 5, but you're not allowed to put 4. So that is also out. But with 14, you can start with 5. So the pair PQ can be 5 and 9, because both of these numbers are between 4 and 14. Or you could have had 6 and 8. So for the sum 14, you've got 2 possible pairs. See, the question is, how many pairs are there? Right. So we got, in this particular case, there are two pairs here. And then for 19, if you look at the pairs which add up to a number between 4 and 14, you can again start with 5. But if you start with 5, then you're going to have 5 plus 14, and you're not allowed to put 14. So you can only start with 6. So you got 6, 13, 7, 12, 8, 11, and 9, 10. So those are the only pairs. And in this case here, there are 4. Right? There are 4 pairs which add up to 19. Are there any which add up to 24? Well, you want 2 numbers between 4 and 14 which add up to 24, so they must be quite large 11 and 13 will work. And so both of them are less than 14 and they are not equal. So this gives you one more. And 29, you can't have two numbers both less than 14 to add up to 29 or anything bigger, because the largest possible number you're going to have is going to be smaller than 28. See, both of them are less than 14. All right, so the rest of them are out. So these are the only possible numbers, and there are 2 plus 4 plus 4 plus 1, and that is 7. Okay. Let's get on to the next problem. The next problem is the following. Question 2. Consider the cube given alongside. Show how to place the numbers 1 to 8 at the vertices of the cube. Now there are 8 vertices and 4 at the top and 4 at the bottom. So all these vertices have got the numbers 1 to 8. Obviously, they're not repeated because you only got 8 numbers. And the sum of the 4 numbers at the corners of each face of the cube are the same. So when you work out this plus this plus this plus this, you're going to get the same as this plus this plus this plus this, and so on. If you take the faces, there are 6 faces, and each face has got 4 vertices. And if you add those 4 vertices, you're always going to get the same answer. So that is the question. So how can we place these numbers now? So this looks like quite a difficult problem. If you try to put them randomly, you're going to have a tough business because you need to get all of the 8 sums to be exactly the same. So let's try to do the mathematics for this. So we do know that if you add up all the numbers, the whole 8 numbers, we are giving them names and we are placing them at selected vertices, right? If you add up all the numbers, then you're going to get all the numbers from 1 to 8 added. And if you add up all the numbers from 1 to 8, you can do it. The answer is 36. All right, so you've got, if you add up all 8 numbers, it's 36. But notice that the numbers are at the top is the same as the numbers at the bottom. Because they say that the sum of the 4 numbers at the corners of each face are the same. So these 4 numbers here add up to the same as this, and the whole lot of them add up to 36. So we can conclude that A plus B plus C plus D, that's the top one, is equal to E plus F plus G plus H. These two are the same, and they add up to 36. So it means that each of them must be 18. All right, so you got 4 numbers which add up to 18, and all of them are from 1, 2, 3, 4, 5, 6, 7, 8. Okay, all right, so A plus. Now, the other interesting thing here is that if the numbers on that face add up to the same numbers as this face here. All right. So then this is common. So it means that A plus D, those 2 numbers added to this, is the same as those 2 numbers added to the same thing. So A plus D must be equal to F plus G. So if I put F plus G plus H in the front, then those 2 numbers are the same when they add up. Okay. Okay, so let's see what these pairs add up to. So suppose I take A plus B A plus B plus C plus D is 18. So you can start off with A plus B equal to 5 because you've got 1, 2, 3, 4, 5. Now, this pair, A plus B, let's look at this top face, right? Those two numbers and those two numbers altogether, they add up to 18. So I could have 5 and 13, or I could have 6 and 12, or 7 and 11, and so on, right? So let's take 5 now, okay? I'm going to take two numbers which add up to 5 and see what I can do with that. Um, let's just draw something here. Okay, I'm just redrawing this cube. I'm going to put add two of those numbers to get 5. So suppose I take those two and I say they add up to 5. I could have 1 plus 4, for example. Right. So then these two numbers add up to 13 because all the numbers at the top add up to 18. You could have 6 and 7. So those two numbers add up to 6 and 7. And here, those two numbers here add up to 6 and 7 also. Add up to 13. So you can have two ways in which you can add to 13. You can have 5 and 8. You're not allowed to repeat numbers. You can put 5 and 8 here and put 6, 7, 7 there. All right, now the question is now, where do these numbers go? Can I put 8 here? If I put 8 here, then I've got 4 plus 8 is 12. And already I've got either 6 or 7 here. That would be too much. I need to get 18 altogether. So I can't put 8 here. I'll have to put 5 here, right? Okay, so if I put 5 here, 4 plus 5 is 9. And I can put a 6 here. And that's fine. And I can put 7 there. So those two will add up to 18. So I've got 5 and I can put an 8 here. So you got 4 plus 6 is 10 plus 5, 15, and I can put a 3 here. Okay, so far everything is going quite well because no two numbers are being repeated. That's the most important thing. So you got 1, 7, 8, and 8, 16. So there's a 2 here. So that's fine. We got 2 plus 3 is 5, 5 plus 5 is 10, 18. And here too you got, so that's it. So here's a solution. You've got A, B, C, D, E, F, G. I think if you try, I tried 1 plus 4. I think if I tried 2 plus 3, I would have gone onto that line there. And I would have come to the same conclusion. So in this picture here, you can see your A, B, C, D, E, F, G. You can just write those numbers down. You got 7, 6, 4, 1, and E, F, G, H, starting from the top there, is 2, 3, 5, 8. So that's a possible way of arranging, getting those 8 numbers. Okay, so let's go on. So the important thing is that just logically trying to figure out what are the equations here and coming to some conclusions. Right? In this particular problem, if I add all 8 numbers, I know what it is, and I know that 2 of those sums are the same. So then each one is 18, and that really it pushed me to solving the problem. Okay, so let me get on to the next problem. Question 3, find all real solutions to the equation x plus 2 raised to the power of 5 minus x equals 1. All right, now this is an exponent problem, right? Now, the only time we have an exponent problem equal to 1 is where the base is 1. You have 1 to any power is 1. Or you could have the index is 0. I don't know if you are aware, but if you take any number and if you raise it to the power of 0, you get 1. Any number. Right? This is done in grade 9, I think, but just take it for as read for those people who are in grade 8. Any number to the power of 0 is 1. There's one other case where you get the base is neither is not 1, but negative 1. But then you'll have to have an even number here. Negative 1 raised to an even power is 1. Because negative 1 squared, for example, is negative 1 times negative 1, and that is 1. That's even. And if you take for the fourth power, again, you have 4 negatives, and that will still give you 1, and so on. So there are 3 possible cases. So the first one is where here you got x plus 2 equals 1, and x is equal to 1 minus 2, and that gives you negative 1. Here, where the index is 0, so the index is, or the exponent is 0, so that gives you another solution. So far you got 2 values of x which will work. And then you have where the index, where the base is negative 1. X plus 2 is negative 1. And then in that case, x is equal to negative 1 minus 2. So x is negative 3. All right, but you must just check to see, is the index even? And 5 minus x, that's your index in this case, is 5 minus negative 3, that's 8, and that's even. All right, so in other words, this is a solution. X equals negative 3 is also a solution because it gives you the base negative 1 and an even power. So there are 3 possible solutions, negative 1, 5, and negative 3. Okay, so that takes me to the next problem. Question 4. No digit of the positive integer n is prime. All right, prime numbers are 2, 3, 5, 7, and so on. However, n is exactly divisible by all single digit primes. Now, what are the single digit primes? Single digit primes. Single digit primes are 2, 3, 5, and 7. 4, 6, 8, and 9 are they're not prime. Okay, so these are single digit primes, and they all are factors of n because n is exactly divisible by those 4. All right, so every one of them, so n, in other words, n is a common multiple. It's a multiple of each of them. And you say that's a common multiple, one number, which is a multiple of all 4. Now, the lowest common multiple, LCM, the literal meaning of LCM is lowest common multiple. That's what LCM stands for. You can work out the LCM of this, but because all of them are prime, it turns out that it's just the product of the four numbers. Right? When you work this thing out, you get 210. So the lowest common multiple is 210. But you want them to be four-digit numbers. And 210 is not a four-digit number. It's a three-digit number. Right? So we are not saying n is the lowest common multiple. We are simply saying n is a common multiple. Now, one very useful fact is that n is a multiple. Any number is also a multiple of the LCM. This always works. If you've got a couple of numbers, any common multiple is not only greater than the lowest common one, but it's a multiple of that one. It's a multiple of that. So you've got n, the possibilities for n are 210, but now this is out because it must be a four-digit number. So to get to a four-digit number, first time you come to it is times 5. When you multiply this by 5, you get 1050. And if you multiply it by 6, you get 1260. If you multiply it by 6, you get 1260. So the possible values for n are multiplied by 7, multiplied by 8, multiplied by 9. When you work all these things out, these are the numbers that you get. But now you want to know which is the smallest. This is out because it's a four-digit, three-digit number. But now you also know that no digit of n is a prime number. Right? None of these is a prime number. Now, you can eliminate this because one of the digits of this number is 5, and that's a prime number. Here, one of the digits of this is 2, and that's a prime number. It says no digit is prime number. Here too, one of the digits here is 4. I'm sorry, is 7. That's a prime number. Okay, now this is fine, 6 and 8. And 1 is not a prime number. Just remember that. Huh? And neither is 0. 0 and 1 are not prime numbers. Right? That's just a convention. Because if you talk about prime numbers, you're starting with the lowest prime number is 2. It's neither 0 or 1. So this works. Right? And it's the smallest. Don't have to worry about the rest. So the answer is, because we took the first few, eliminated all these, the smallest ones, and then we came to this. So that must be the answer. Okay, so that takes care of question 4. And now we go on to question 5. Now what is question 5? Question 5 says, question 5 says the following. Sorry, just had to pause there. Okay, this, I'm not going to read all these things here, but what it says here is the following. You've got a cube like this, which has got 20, let me just, You got this cube here. Oh, yeah, yeah. You got this. You got this cube, which is made up of a lot of small cubes, as you can see. And at the top of this, you have another cube, but the top face is painted. It's painted red, wet paint. Now, what happens now is that this single cube is rolled along the faces of these of the larger 3 by 3 by 3 cube. So when you roll this thing, it falls here, for instance, and then once you have that, you can roll it again, and there's a direction in which it is rolled. Comes here, then it's rolled that way, then it's rolled that way, roll that way, roll that way, and so on. So you keep rolling it in different directions like this until you come to this point here. So in other words, you cover every possible square. There's every possible square, there are 27 of them, and you come back to the starting point. And the question is now, the paint, only one face is painted. As it goes onto these, some of these things will be smudged with paint, especially if the top, only when the top is hitting the floor, then that part will be painted. So whenever the red paint falls on the floor, right, that part has got paint in it. So the question here is, how many squares will be red when the small cube reaches the end of the path? This is a star. So in other words, where does the paint actually fall? So what they do is they say, look, let's call that face there 1, right? And then we'll keep track of where 1 falls. Like for instance, the first time when you roll it this way, the 1 is facing here. It's a vertical face along this line here. And you roll it again onto this, you'll see that the paint actually falls here. So this is the 1 here, right? And it falls on that. So therefore that paint, this space here will be red. And then after that, you move in that direction. And you go on like that. Now, you see, if we need to keep track of all these. There are 6 faces there, and they are all over the place. So to keep track of them, you give names to these faces. Like the way you'll give it is like the way you have a die, you know, when you play Ludo or something like that, you'll see that you have to throw dice. And now in any dice, I don't think you are aware, or maybe you might be aware, that these numbers 1 to 6 are not random. If this is 1, then the opposite face is 6, because the opposite faces in a die always add up to 7. You can check this thing out. See? So if you call this 5, then the face opposite there is 2. And if you call this thing here 3, for instance, then the face which is facing that way, opposite that, is 4. So if you can see 3 faces, then you know what the other 3 faces are in a cube. So suppose you name these faces like what you have done here, 1, 4, 5, and this is a solution. I'm not going to go through this. It's very tedious. And to be quite honest, I couldn't keep track of this thing. I couldn't keep track, but I'm sure some of you can. And then they tell you which face is at the bottom. The numbers here, like for instance, when you roll it once, the 4 goes to the bottom. And when you roll it again, the 1 goes to the bottom. I pointed that out, the 1 goes. So this is a red face. So if you keep going on like that, you have to see where 1 is. 1 is here, and 1 is here, but there's no other places you get 1. The red face only goes into 3 other squares, and those are the only ones which will get smudged. The rest of them don't. Okay, so I'm not going to go through that process. You understand what the problem is, and you can go and try it out. Okay, so that now takes me to the next one. Okay, question 6. Now let's see what question 6 is saying. Question 6 is saying the following. A triangle, this is the triangle here which is in the question, is divided into strips by drawing equally spaced lines which are parallel to the base as shown. So you got all these are equally spaced, and you got all these lines like that, right? And the alternate strips are painted the same color. So you got blue, 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 and red, so like this. And you know that the area of all the blues, if you add them up, the area is 90 square units, right? So you don't know what a unit is, but whatever it is, it may be square centimeters or whatever. But all these add up to 90. They're just the blues. And the question is, what do the reds add up to? So if you look at this picture like this now, it's not easy to see what the reds will add up to. But if you think of it carefully, you'll see that I can redraw this thing so that this tiny little thing is repeated several times. See? And to do that, what you have to do is to draw parallel lines. Like from here now, I'll draw a line which is parallel to that, like that. And like that, I do all the parallel lines this way. And this side also, I draw lines which are parallel to this. And I get this picture here. Right. Now I got a beautiful picture here. And all these triangles are all exactly the same area because these are all equally spaced, you see. And then you can prove, well, it may take a little bit of time, but you can prove that all these little triangles are identical. See? Like you can prove, by identical means that they're all congruent. You can check this uh, it out in the small triangle, but I'm not going to go into that. So in other words, we've got this triangle is all broken up into all of equal sizes. So that helps a great deal because I don't know what the area of each one of them is, but let's suppose the area of this is X, right? That's the single unit. I'm not going to say it's equal to 1. I'm going to say it's X square units. All right, so then this will be 3x. You can see x plus x plus x, right? And you'll see this is 5x here. Right? But the point is that without having to draw it as I did, you can still say the next one is 7x because each time you see you're going to add 2 new squares on the flanks here to the previous one. See? So yeah, you see, this part here is exactly the same as the second line. See, this second line is exactly the same as this. So what we are doing now is adding 2 more squares. So each one is obtained by adding 2 more. So So you got 7x, 9x, and so on. Okay, we might as well do it. 11x, 13x, 15x, and 17x. Okay, now we know that all the blues add up to 90. So the blues are the x. The next one is 5x. X, 3x, 5x. X plus 5x, we keep adding 4x. Until you go to this. Oh, wait a minute. Oh, no, this is not 11x. It's 13x. Sorry, I must keep adding 4x to this. And I made a mistake and added 2x there. Should have added 4x. So you get 13x plus 17x. As you can see, 17x is the last one, and that's blue. Now this, when you add up all this, you're going to get 90, because they say the blues add up to 90. So that allows you to calculate the x, right? And you'll see that this is 45x on the left-hand side, and that gives you a very nice value for x. X is equal to 2, right? So now what these are the blues, and the reds, right? The reds will be, have to start with the second row, so that's 3x, and keep adding 4x. Right? So there are 4 reds here, you can see, and I've got 4 numbers here. And this is actually 10, 21, 36, but we know that x is 2. So therefore, 36 times 2 is 72. Square units. We don't know what the units are. Could be centimeters, millimeters, meters, whatever. So we just call them units. All right, so the idea here was just to split. This often happens when you, in an area problem like this, try to break it up into all smaller units so all of them are the same. And then that'll give you an idea of how to actually calculate the areas. Sometimes you have a square, and then, so the trick is to divide them all into smaller squares so that all of them are the same size. All right. So the next problem is question 7. Now, it says in the right angle triangle ABC, or these names were not put in, doesn't matter. It's called ABC. AD is 5, and FC is 3. Okay, this is E. All right. DEFB is a rectangle. So this is a rectangle here. And you're given this, that, you're given that, and you're asked to find the area X of the rectangle. So you're asked to calculate the area of this rectangle. All right, now how do you do that? Well, the area of a rectangle is length times breadth, and we know neither the length, let's call it A, or B, the breadth. We don't know these two numbers. So the question is, what is AB? So using the given information, this is 5 and this is 3, we need to calculate what AB is. All right, now the way to do this is to use what we call similar triangles. In other words, two triangles which have got the same angles. You see, when you study congruency, two triangles are congruent. You've got various conditions for congruency. You've got 3 sides, You've got two sides and an included angle. You've got two angles and a side. And you've got right angle, hypotenuse, side. But in every one of them, you have a side. You don't have a case where you got three angles. So three angles of one triangle equal to three angles of another does not make them congruent. See, you can see in this picture here, you got this. This is just a small version of that one. If you take a photograph of a large triangle, the small triangle will have exactly the same angles, although they will be different sizes, have the same angles. So yeah, in this triangle here, I've got a black dot, and I've got a circle, and I've got a cross. Here I've got a black dot, a circle, and a cross. They've got the same angles. Now, one of the very interesting thing about these triangles are said to be similar. They're not congruent, but they are similar. That's the word that is used to describe two triangles which have got the same angles. You will study this similar triangles at a higher level, maybe grade 11, perhaps even in grade 10. But one very obvious fact about this is that one is just an enlargement of the other. Like, for instance, if I know that this is 3, and if I know, okay, if I know that this is 3, and if I know that this is 5, and this is 6, then I can, and if I know that this is 1 here, then I can calculate these two sides, right? Because one is just an expansion of the other one. Now, this thing here, this side here is opposite cross. And here, the side opposite cross is 3. So you'll see that the side opposite cross here is 3 times the side opposite cross here. So that same increase will work right throughout. So like the side opposite dot, black dot, is 5 here. So the side opposite here will have to be 5/3, right? So in other words, to get to 1, I have to divide this by 3. So likewise, the 6 I have to divide by 3, and I'll get 2. So this is 6 is opposite circle, and opposite circle, it'll be 6 divided by 3. Okay, so here it'll be 5 divided by 3. So they're in the same, what you say they're in the same proportion. See, in general, if you have you notice they are in the same ratio, as it were. So you'll have B, let's make it A. A over, now the important thing is here is that A corresponds to black dot. If you've got two similar triangles, you think of them in pairs. A and dot, B and cross, C and circle. So A corresponds to dot, and A over the side dot is R, is equal to B over, it corresponds to cross. The cross here is Q, B over Q, and finally it's C over P. And so when you got two similar triangles, you always have this kind of a ratio, right? Now, to get to this thing here, you will see that there's a 90 degrees here, and there's a 90 degrees here, and you've got this angle, call it dot. Now these two lines are parallel because they're the opposite sides of a rectangle. So this dot here is actually equal to this dot here. These are corresponding angles. See, line is parallel, line is parallel. You drop this thing down. So you'll notice that these two triangles have got the same angles. Dot, 90 degrees, and of course the remaining part, these are also corresponding angles. See? So they got the same angle. Then, in fact, it's useful to know that whenever you got a triangle and if you draw a line parallel to one of the sides, the small triangle that is created is always similar to the large triangle because these are corresponding angles and they will be the same. See, whenever you draw a line parallel. So this is what happens here. You got a line parallel to that. So those two triangles which are created are similar. Okay, so that allows us to solve the problem because this is a rectangle. So this part here is A, opposite sides of the rectangle, and this side here is B. Let me just clear out these. And so you got, this is A, and this is B. So if you look at this triangle here, it's 5 is opposite cross, and opposite cross here in the small triangle is A. Right? And this triangle here, if you take B, that is equal to B over, that's opposite dot, and this is dot here, and it's B over 3. Because the side opposite dot is 3. So now you got that thing there, so that immediately tells you if you cross multiply, you get AB equals 15, and that is exactly what we wanted. Right? Without knowing what A and B are, we can calculate what the product of A and B are by using similar triangles. So the answer to this problem is 15. Okay, so I'm going to go on to the next problem. In this problem, the odd digits 1, 3, 5, 7, and 9 are constructed of matchsticks, as shown. So you can see, actually, if you make it big, you'll see there are two matchsticks here. So the one is made up of two matchsticks. The 3, you've got 1, 2, 3, 4, 5. The 3 horizontals, even in 5, and 2 verticals. And here you've got 1 horizontal and 2 verticals, making 3. Here we've got 3 horizontals and 3 verticals, so you got 6. So the number of matchsticks for 1, 3, 5, 7, 9 are 2, 5, 5, 3, 6. That's what I've got here. Right? The number of matchsticks used is 2, 5, 5, 3, 6. Okay. Now, they say using each digit only once. These are the digits 1, 3, 5, 7, 9. How many 3-digit numbers are there having the sum of their digits greater than the number of matchsticks used to make that number? Now, that's quite a mouthful. Okay. So the question is now, how many 3-digit numbers can you make using these five numbers? All right, now this is a problem on counting, and I need to tell you something about counting, and I'm going to try to see whether I can get a blackboard here. Doesn't seem that I can get a blackboard. I thought I can get a blackboard, a whiteboard at least. So all right, we'll have to do without it. Okay, let's just pause for a moment and ask ourselves what's going on here. I want to make a 3-digit number using these 5 digits, and each digit must be used only once, right? So how do you go around doing it? You can say, all right, the first digit can be 1, right? If the first digit is 1, a 3-digit number, it can be, there are many numbers you can have, but there are 5 possible ways in which you can choose the first digit. It can be 1, 3, 5, 7, or 9. So the first digit can be chosen in 5 different ways. Now, once I choose the first digit, then the second digit, you're not allowed to repeat. So it could be, the second digit could be 3 or 5 or 7 or 9 in this case. Right? And here too, you got 4 possibilities. This time it'll have 1, 5, 7, or 9, and so on. In 7, you'll have 1, 3, 5, and 9. But in each of these cases, you got 5 cases, you've got 4 things shooting out. So the number of 2-digit numbers, let's just do this. 5. You're going to get 20 because you got 5 plus 5 plus 5, 4 plus 4 plus 4, 5 times. So it's 5 times 4. 20 2-digit numbers you can make. 1, 3, 1, 5, 1, 7, 1, 9, 3, and so on and so forth. You can make 22 2-digit numbers. But once you choose the second digit, the third digit, you can choose it in only 2 possible ways. 3. Because if I chose 1 and 3, for instance, suppose I chose 1 and 3, then the third digit can be 5, 7, or 9. So here, for each of these 20, I have 3 prongs shooting out. See? So there are actually 60 numbers altogether. So the argument is the first digit can be chosen in 5 ways. For each choice of the first digit, there are 4 choices for the second. So therefore, the first 2 digits can be chosen in 5 times 4 different ways. First 2 digits is 13. There's 20 different ways like that. And for each choice of these 20 numbers, 2-digit numbers, I have 3 ways in which I can choose the third digit. So that makes me 20 times 3, which is 60. So there are 60 numbers that you can form using those 5 digits. Okay? All right. So that's the first thing. I'm just going to wipe that out because I don't have space. So there are 60 numbers. We can create 63-digit numbers. From 1, 3, 5, 7, 9. Right. Now, you want from these 60 numbers now, you want to know how many of them from the 60, how many of them have the sum of the digits greater than the number of matchsticks used to make that number. Now, what I'm going to do is actually, you see, if you take 135, that's one of the 3-digit numbers you can make using the letters 1, 3, and 5. Now, those numbers can be mixed around by 153, the 153, 513, 531, 315, 351. So you can make 135, 153. Starting with 5, you can make 1331. Starting with 3, you can make. So there are 6 numbers you can make using only those. See? And if I choose something else, like 579, I can make another 6 numbers from that one. But now, if I'm interested only in the groups, right? Not because you see, this group here, the sum of the matchsticks in this group will all be the same, because the 1 will have 2 matchsticks, the 3 will have 5 matchsticks, and the 5 will have 5 matchsticks. So there will be 12 matchsticks for the number 135. You see, it says the number of matchsticks used to make that number, that 3-digit number. So this 3-digit number requires 12 matchsticks. But all these will require 12 because they're using the same lot. So what we do is we just count 135 only, and we know that there are 6 numbers which are associated with 135. But I'll just take 135 because that particular one has got a specific total, right? Another grouping, 357, will have a different total. So what I've done here is I've taken all the different, you see, there are 60 altogether, right? And these 60 numbers are divided up into groups of 6. See, 135, there's a group of 6. 579, there's a group of 6, and so on and so forth. So the number of groups that you have is 60 divided by 6. 135 is not repeated anywhere. And if you just work out the groups, then you will see that there are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 groups, and each group can be turned around in 6 different ways to get 6 new numbers. And altogether, you'll get 60. But there are 10 groups. Okay, so I'm interested in the group right now. See, the way I write the groups is like this. I got 1, 3, 5, 7, 9. Right. On the write down the 10 groups. I'll start with 1. 1, I'll put the second one as 3. 1, 3, 5. Then I'll put 1, 3 again. And then you'll have 7. I'll put 1, 3 again. And I get 9. So 1, 3, 5. 1, 3, 7. 1, 3, 9. So I've dispensed with 1, 3. Now I go to 1, 5. 1, 5. I'm not going to use 3 again because I've already got 5, 1, 3 there. So 1, 5, it'll be 1, 5, 7 and 1, 5, 9. Right? So 1, 5, starting with 15, you get 1, 5, 7 and 1, 5, 9. Right? That's it. Or you can go to 17, 1, 7, 9. Right? So these exhaust all the ones which have got a 1 in it. So now I take 3, ignore that one. With 3, I'll go to 3, 5. First 2, I go 3, 5, 7 or 3, 5, 9. This is the way you list your numbers. 3, 5, 7 or 3, 5, 9. I'll finish with 3, 5. I can go to 3, 7. So I'll go 3, 7, 9. That's all. Right. So that finishes the 3. And then I can do 5, 5, 7, 9. If you look at this now, you got 6 and 4, 10 here. And these are the 10 numbers I've got. Now in each group, they say the sum of their digits. So we need to calculate the sum of the digits. That's why I got the digit sum here. You can call this digit sum. 1 plus 3 is 5. 1 plus 3 is 4. 4 plus 5 is 9. And so I've listed all the sums here. And likewise, I've counted the number of sticks that are used to create any one of these. I showed you how to create the sticks for 1, 3, 5. And we saw that there were 12 there. Right? 1, 3, 5. It will be 2 plus 5 plus 5, which is 12. So like that, you count the number of sticks for each one of them using this thing. And this is what I get. Right. Now, I know this. Let's go again to this. How many 3-digit numbers are there that have the sum of the digits, the sum here, to be greater than the number of matchsticks used to make the number? Right. Now, I see here that this doesn't work. The sum is not greater than that. But this sum, it works. This thing doesn't work because 13 is not greater than 13. This works, this works, this works, this works, this works, this works, this works. All these sum of the digits is greater than the matchsticks used. So we want to know now how many of them are like that. So you have to count all the number of ticks here, which you got 1, 2, 3, 4, 5, 6, 7, 8. So the 8 groups, right, where the sum of the digits is greater than 10. But each group can be created. You can create 6 numbers out of each group. So 137, as we saw, well, 135 didn't work, but 137 will have 6 numbers. So those 6 numbers will all have some 10. And every one of these, there are 6 numbers. So you got 8 times 6 is 48. So there are 48 numbers which satisfy this condition, and 12 of them don't. Those two, each one of them will got a 6 there. Those numbers you'll add up, you see the number of the digit sum is smaller than the number of 6 used. So the answer is 48. All right, so you have to understand what this question is to solve the problem. Okay. Now, all of you are listening. I hope you know that you are going to do the 2023 Junior Round 3, and you're going to get the solutions to it. And I trust that all of you have already tried these problems. There's no point in coming and looking into a solution when you don't even know the question. I should have said this much earlier, but always try and keep trying until you fail completely. Then you look at the solutions. I'm simply giving you the solutions to all these problems with the trust that you have actually tried these problems on your own. Okay, question 9. A rain gauge is made up of 2 cylindrical shaped funnels. So this is a cylinder. Right? The actual question in the paper was written differently, and I couldn't understand what a rain gauge looked like. But in the end, I figured out it's going to be something like this. They are both cylindrical shaped funnels. This is a cylinder. By cylinder, you mean it's got a circular cross section, right? Just like a chalk or a can or something like that. Those are cylindrical shaped. Now, 16 millimeters of rain falls into a funnel of diameter x. Right, so here the diameter is x. And the rain falls into this. Right? And 16 millimeters. So when you measure the height of this, right, you're going to get 16 millimeters. And this water drains into another funnel having radius 4 centimeters. So yeah, this is the radius is 4. So the diameter is 8. If the height of the water in the second funnel is 49 or 4.9 centimeters, this is 16 millimeters here. So the units are different, 16 millimeters, and here you got centimeters. So one must be careful. So this is 4 centimeters here. Right. So it drains, all this water here drains into this, which means that the volume of the water in this, the volume of the water here is the same as the volume of water here. But in this diagram here, the water takes the shape of a cylinder. And here too, the water takes the shape of the larger cylinder. Water has got this property. So now we want to know the volume of the water here is the same as volume of the water here. So the only thing that we have to ask is, what is the volume of a cylinder? So there's a formula for this. The volume of a cylinder, in fact, many of these shapes which have got a cylindrical shape, like all cross sections are the same, is the area of the base times the height. And this always happens. Even a rectangular thing, the volume of a rectangle, a box is area of base times height. Yeah, it's area of base times height. No matter what kind of shape you'll get, if the bottom shape is exactly the same as the top one, then you got a cylindrical kind of a thing, and the area is area of base times height. So here the area of the base is the base. The diameter is x. The base is a circle, and you know the diameter is x. The area of a circle is pi r squared. So if the diameter is x, the radius is x over 2. So you got pi times x over 2 squared. That's the area of the base, multiplied by the height, which is 16 millimeters. I'm going to convert that to centimeters because we're working in centimeters right throughout. And that is equal to the area of the water in the lower cylinder. And that is also the area of a cylinder. And the area of that cylinder is the area of the base there is pi, and the radius is 4 centimeters. That's okay. Pi r squared, pi 4 squared, times the height, which is 4.9. Right. All in centimeters. So you need to calculate x in centimeters. The pi's cancel. You got x squared over 4. I'm just going to put x squared over 4. So I'm going to multiply this by 4 to get, and this is 4 squared, 4,9, and I'm going to divide that by 1,6. Right? I've got x squared over 4 here. So I'm multiplying that by 4 and divide by 6. You can make this thing 49 if you don't like decimals. But multiplying this by 10, multiply this by 10. So you've got that. Okay, so you got so 4 squared is cancels, 16, 16. And you're left with 4 times 49. So x squared is equal to 4 times 49. So x itself must be equal to 2 times 7. I got a nice square root. Square root of 4 and square root of 7 gives you 14. So your x is 14 centimeters. That x there is 14 centimeters. Okay, I don't know whether I made a wrong calculation here, but I don't remember this answer. Seems to be okay. All right, so let's get to the next problem. The problem was to find x, so we just found it. Let's get to the next problem. Now we go to question 10. Question 10 reads the following. The numbers 2, 6, and 7 in the face of a clock are joined to make a triangle as shown. Right? And then these are joined. And they ask you, what is the value of x? I just want to show you something. You got the face of a clock here. Now, the problem is that you got numbers on the clock joined. And how do you know what these angles are? Huh? The thing to observe here is the following, that all these numbers are spaced equally apart. So that's a starting point. That they all are spaced equally apart. So I'm going to take the center of this clock and join it to any two of these numbers, 1 and 2, for example, two consecutive numbers. Right, so what is this angle? We can actually calculate this angle. The reason being that you can divide this entire thing into 12 pizza slices. All of them are equal because you're joining 2 and 3, 3 and 4, and so on. So 12 of these angles will make 360. If you go right down, you'll have 12 of these pieces. Make 3. So each one is 30 degrees. Right? So you can calculate the angle made by any of these. If you take the triangle there, then the angles of this triangle can be calculated, because this is 30, and remember, this is a radius of a circle, so all of them are equal. So you can calculate the angles like that. So now to calculate x, again, we do the same thing. We look at the center, right? And then I join it to okay, so I know, bearing that in mind, what can I calculate? Okay, what I'm going to do is I'm actually going to join these. Join that. And join that. Then what I see is the x now becomes one of the angles in a quadrilateral. And I can see what this angle is between these two lines which I have drawn. Because if I join it to that, I get 30. If I join it to that, I get another 30. If I join it to this, I get 30. Join to that. So there are 1, 2, 3, 4, 5. So this is 150. It's made up of 5 30 degrees. See? As far as x is concerned, it's made up of two angles. Let me join this. Like that. Now I see that the whole angle is 150. From here to here, there are 4 30s. 1, 2, 3, 4. So this angle, this triangle here, it's an isosceles triangle, joining O to 2 and O to 6, right? And I can calculate this angle here, because this angle here is 430s. 1, 2, 3, 4. So this angle here is 120. So this angle here is, to get that one, it's 180 minus 120 divided by 2, because you've got an isosceles triangle here. So this angle here, yeah, I'm really interested in that angle. That angle is 180 minus 120 divided by 2, because it's part of this triangle, which is isosceles, and we can calculate this angle here. And likewise, now this is added. So x is actually equal to that shade added to this one. These colors are becoming quite useful here. So added to that, x is equal to the sum of these two angles. And this angle here we can also calculate, because it also belongs to an isosceles triangle. But this time, it's this triangle here. Join O to 7, O to 6, and these two are equal because they are radii of a circle. And this is a base angle. So the angle inside is 30 degrees, because this is just between 6 and 7. So this is 30 degrees. These two equal angles add up to 180 minus 30. This is 30 degrees. 180 minus 30 will give you the sum of these two angles. But these angles are equal because you've got an isosceles triangle. So each one of them is 180 minus 30 divided by 2. So x is actually equal to this, the calculation. It's a sum of two angles, right? One of them is this and the other is this. If you work this thing out, you'll get 105 degrees. All right, so that's quite a demanding question. It's a question like in geometry, but basically you've got isosceles triangles, and you have to use the fact that in an isosceles triangle, if two sides are equal, then the two angles opposite them are also equal. In any isosceles triangle, if you know that those two are the same, you can conclude that these two angles are the same. It's a very interesting theorem in geometry. And likewise, if you know that the two angles are the same, then you can conclude that there's two sides opposite these angles, these equal angles, they're also the same. So we used isosceles triangles here. At the same time, we observed something about a clock. All right, so that takes us to the next problem, which is question number 12. Question 12 says the following. Oh, it's question 11. Question 11. Yeah. I say find a 5-digit integer, A, B, C, D, E, with no repeated digits, such that A, B, C, D, 1. Oh, it's a 5-digit number. So this is a 6-digit number. This is a 6-digit number. So you put a 1 at the end of the 5-digit number, you get a 6-digit number. And here you got a 1 in front of the 5-digit number to make that also a 6-digit number. And this 6-digit number is equal to 3 times this 6-digit number, which starts with 1. Right. Now, how do you find this integer? It looks it's very complicated because you've got 5 unknowns. But you can solve this problem beautifully by saying you actually don't have 5 unknowns. You've got only 1 unknown, this 5-digit number. So you'll start off by saying that let x be the 5-digit number. A, B, C, D, E. Now, this is not a product, it's a 5-digit number. It could be 61342 or something like that. Right. So these are all digits, A, B, C, D, E. They are digits, and this is a 5-digit number. All right, now you got an equation here. Can I write this in terms of x? The answer is yes, because if I took in fact, if I take anything, say 136, right? This is 10 times 13 plus 6, 136. If I had 1365, then that is equal to 10 times 136 plus 5, because it's 1360 plus 5. See? So here too, this is A, B, C, D, E, 0 plus 1. This is first number. Is equal to 3 times. Now what about this? This one is a little bit trickier because you got a 1 in the front. So this time, that's your number, 1 in the front, right? So what is it? This is actually 100 plus 36, 136. And if I had 1365, and if that is my x, I've got 1 in the front, it's 1000 plus 365. Okay? So you got an x here. So this is 3 times. What is this number? This is 1 with 5 zeros. 1 with 5 zeros. 0, 0, 0, 0, 0, plus your A, B, C, D, E, like what we saw here. See, 365 or 36. So that's your x. Right. So you got, this is 10x, because you're putting a 0 at the end of A, B, C, D, E, sorry. So 10x plus 1. And here, this is 100,000, 5 zeros. So it's 300,000 plus x. You got a single equation with one unknown. And the unknown is x. That's exactly what we need to find, this 5-digit number. So, you got 3x, yeah. Sorry. I got a 3 outside that bracket. I should have had 3x. 300,000 plus 3x. Bring the x's to one side. 10x minus 3x is 7x. 300,000 subtract 1, you get 289,989. Right? And therefore, 7x is equal to this. So x is equal to, if you try to divide this by x, 7, you get exact answer. It goes exactly. It's 142,857. Right? 289,989 divided by 7 gives you this answer here. So that is how you do this problem. There are many types of problems like this, but just study this thing carefully and see the strategy, the way we get an unknown and we use that unknown to describe your number in terms of that unknown. But you have to think very carefully and do some examples, and like the way I've done, and see what is going on here. And then once you get the pattern, then you will say, oh yes, now I know what the equation is. See? So that is the strategy. Always try to use some small numbers, get a feel for the problem, and then after that, you can uh, get the equations. Okay, so the next problem is number 12. Now this is an arithmetic puzzle. You've seen this, where you've got a 6-digit number and you're adding it to itself, tick tock, tick tock. And when you add it, you get install. Each letter stands for a digit. So you got a 6-digit number here. So there are numbers from 0 to 9. And a single symbol, you must use the same letters for those symbols. All right, so I've drawn lots of things here so you can sort of track this. So what can we conclude? For the first thing I conclude is that this I here must be 1, obviously, because you can't have these two numbers adding up to something which is more than, you can't have 20s here. All right, so the I is 1. So I'm going to put a 1 here. Likewise, there's a 1 which goes in here. Right? Because the I's are there also. So now you have to start thinking. If you look at this thing carefully, you see you've got a double L here. Right? Also, you've got K plus K here. You've got the same thing added to get an L here. You might have to carry over, but this L has to be even because it's K plus K, 2K. So L is an even number which is repeated here. So that gives you an idea as to how to proceed from here. So suppose you've got 22 here. Well, it can't be 0 for one thing, obviously. Otherwise, you'll have everything is 0. So suppose you got 22 here, right? LL. Now 11 plus 11 is 22, but you can't put 11 here because these are two separate numbers. So now the question is which two-digit numbers ends in 22, right? So it has to be 122. 61 plus 61, right? It can't end in 222 or bigger because you got a two-digit number. Two-digit numbers will have to be, when you add them, it's going to be less than 200. Right? So I could only have 122, and each one will have to be 61. Okay, suppose I put 61 here. Okay, I got 1 plus 1 is 2. 6 plus 6 is 12. So K is 1 then. It's K. K is 1. Oh, but that's not right because I already got a 1 here. Right. So this is out. I can't have 61 and 61 because the I is 1. K can't be 1. Okay, so that eliminates that possibility. So let's try. It's 22. So remember the thing L is even. So the next one will be 44. So I could put 44 here. Obviously, as before, you can't put 22, but you got 144. The sum of these two numbers is less than 200. So it has to be 72 and 72. Okay, so this is fine, 72, 72. And you got K is 2, so you'll have a 2 here. All right. So now comes an interesting part. You got a 2 here, right? So when you add these two, you're going to get 4. You might have been carrying something over, but the largest value you can get is 5 here. But there's no carrying over at this stage. Because there's no carrying over, this 1 plus 1 is 2 here. There's no carrying over. And that's not possible because you got a new number here. Can't be 2, and K is 2. So we said all these things have got different letters. Each letter represents a different digit. So even 72 fails. Right. So now, how do you go around doing this? You have to go to the next even number. The next even number is 66. Right, now you have, can't be 33. It'll be 166 because these two numbers are less than 200. And both of them are the same, okay. So it's 83, 83. Once again, you got 3 plus 3 is 6. K is 3. So we'll put a 3 here. All right, but there's no carrying over. That's the important thing. 6, it could be, this could be 6 or 7. We don't know, but there's no carrying over. So this 1 plus 1 must be 2 here. See, I didn't put this earlier on because I don't know whether it's 2 or 3. If you had something carrying over, then it could be 3. You see, now I know there's no carrying over. So this is 2. So S is 2. And now, and there's a 1 here. Okay. And now the only thing is now what must you got the same number here right throughout. The TT and you got TT. And you're carrying 1 over 8 plus 8 is 16. You're carrying 1. So what can this possible be? So you can try the different numbers. Already got 1, 2, 3. If I put 4 here, then 8 plus 8 is 16, carrying 1. 4 plus 4 is 8 is 9. 3 plus 3 is 6, which contradicts that. So I can't put 4 here. 5, the same thing. 8 plus 8 is 16. If I put 5, then 5 plus 5 is 10, carrying 1, 11. And I'll have a 1 here, which is no good. So I can't put 5, I can't put 6. I can try 7. Let me try 7. So what do you got? 3 plus 3 is 6. 8 plus 8 is 16. 1 plus 14 is 15. Okay, now that's fine. But then you got 1 plus 6 is 7. Oh, but there's a t here as well. Right, so this 7, 7 works. All right, so there it is. So this is the answer to the problem because the t is also here. I forgot to notice that, but you see that the 7 works. This and oh. So this is also 7 here. T is 7. T occurs so many times. So you're carrying 4. 7 plus 7 is 14. Okay, that's nice. Now no number is repeated. So that's the answer. What is TikTok equal to? It's 713783. All right, so that takes care of problem 12. We got 15 altogether, so this is a long haul, guys. So I can take off all my drawings and I will now get to problem 13, which is this. Right. So here you got a problem here which looks like this. In a square, the diagonals are drawn. Now in a square, you should know all the properties of a square. 45 degrees, all the sides are equal, the two diagonals are equal, and all these angles are 45 degrees. This is 45, 45, 45, 45. It doesn't happen in a general rectangle. In a square, you will have that these two angles are the same. Even in a rhombus, these two are the same, but they need not be 45 because the angle need not be a right angle. In a square, they are 45. Okay, whatever it is, a line is constructed from the midpoint of one side, as you can see, to the bottom vertex of the opposite side, and determine the ratio of the shaded area to the total area of the square. They don't give you any dimensions here. So you can put some dimensions if you like, but I don't think it's necessary. Now, this is problem number 13, so it's usually a demanding problem. How are you going to calculate this area here, a small area, and there are so many other triangles and quadrilaterals here. But for one thing, I do know that all these 4 triangles in a square, the diagonals, When you draw the diagonals, you will get you'll create a four same, all these triangles are the same. They intersect at 90 degrees, 45, 45, 45. They're all congruent, so they all have the same area, and they are exactly the same right angle triangle. In other words, they are congruent, right? 90 degrees, and all these sides are the same. All right, so you got that, all these are equal. Okay, that you know. Okay, so maybe we need to work out this shade here. Anyway, it takes a little bit while to understand this, but we're going to use a theorem. In fact, we're going to use two theorems, uh, which I think you would be the great minds will probably come across it. But now you are doing round three. You guys should know a little bit more about your own school syllabus. And one of the things you do in grade 10, right, is what we call the midpoint theorem. Let me tell you what the midpoint theorem is. Very important theorem in geometry. The midpoint theorem says that if you take the midpoints of two sides of a triangle and join them, midpoints means like the way I've done here now, and join them, then it turns out that that line that you join is actually parallel to this one here. This is a theorem. It's not obvious. That if you join two midpoints of a triangle, the midpoints of two sides of a triangle, then that line segment is parallel to this other one. And more than that, its length is equal to half the length of this. See, if this is 10, this is 20. So that's very useful. That's called midpoint theorem. And I also told you about similar triangles, right? Where if the two triangles have got the same angles, then the sides are in the same proportion. So I think you're going to use all these here. Okay, now the third one, what you're going to use, another theorem in geometry you're going to use, is the following. That if you got a triangle and you got any line from a vertex to the other side, see? With any line from the vertex to the other side, and suppose this other side is divided in the ratio A is to B, it turns out that the area of this triangle over the area of the other triangle, A over B, is the same as small a over small b. When you work out the area of this and the area of that and put one over the other, you're going to get a over b. Now this is quite obvious here because this is half base times height. The area of this triangle here, half base times height. But this triangle got the same height, you see, because they're both from the same vertex. So this area here is also half base times height, half BH. So when you put one area over the other, A over B, the half and the H will cancel off, and you add A over B. Okay, so that's a quick way of explaining why the ratio of the areas is the same as the ratio of the sides. All right, so that tells me that if we need to work out the area of this, I need to know the area of this, because the area of this over the area of this is equal to that over that, you see? Right, so we're still a little bit some distance away from actually solving the problem. Because one of the things that we have to do here is we need a construction here. See, I got a midpoint, and I'm going to use the midpoint theorem to solve this problem. And to do that, I've got a midpoint here and I've got a triangle here like that. So why don't I draw a line from here parallel to this? Oh, okay. Anyway, this line is parallel to this, which means that from the midpoint theorem that I told you earlier on, we got a parallel line. That means these two are now equal. Okay, so that's quite useful because if you call this side A and you call it the side A, then that means this thing here is 2A, which means that this is also 2A. This side here is 2A. And likewise, mm, and this whole thing here is 2A also. So if this thing here is B, this part here, right? Then if you look at this picture here, and this is a little bit difficult to see. I'm looking at this triangle here. This one here. And then I've got a line parallel. And earlier on, I told you you've got a line parallel. Then the ratios are the same. So you got this small triangle is similar to the large triangle. They got the same angles. So this is 2A. There is A here. And I've got B here. Which means that if you take the small triangle, it's got the same angles as the big triangle, 2A over 3A. This over the whole thing is equal to, let's call this thing X. It's equal to B over X. Because B is opposite this point here, and X is opposite that. So these two triangles have got the same small triangle. This triangle here, which is shaded, has got the same angles as that triangle. So therefore, the A's cancel, and so the X, 2X is equal to B. So you get 3B over 2. So X, 2X is equal to 3B, X is 3B over 2. So this thing here is 3B over 2. That one there. Right? And now by the midpoint theorem, so this is 3B over 2. So this whole thing will have to be twice that. Remember I told you that this is equal to half of that. So if this is 3B over 2, this whole thing is 3B. If the whole thing is 3B, this part here is, this is B, so this will have to be 2B. Right? So this 3B over 2, this whole thing is 3B. This part is B, so this part will be F. Now you got the ratio of this over this is 1:2. So if we need to calculate this area here, let's call it capital X, right? Is the area of this. This over this, I told you this over this is the same as the area of that over that. So if this is X, this length here is twice that. So therefore this area is 2X, like that. So now we have the area of this quarter circle is 3X. That's what I got here. I'll put 3X here. Now I said the whole thing is all of them are 3x, so the area of the entire square is 12x because each one is 3x. And we needed to work out the ratio of the shaded area to the total area. So the shaded area we called x, and the total area is 12x, right? The x's cancel, and the ratio is 1 over 12. But this is quite a tricky problem. I think there may be an easier way of solving it, but I haven't seen it. Say, like for instance, now this is 2a here. So we should be able to work out the area of the whole square in terms of a, because this is 2a, so all these diagonals, all these will be 2a. So by Pythagoras, this is square root of 4a squared plus 4a squared, which is 8a squared. And therefore the area of the square is 8a squared. So that's quite useful. So we need to work out the area of just this part here, x, in terms of a. But I don't know, that may be a little bit difficult to work out, the area of this in terms of a. You'll still need the midpoint theorem. All right, so that is quite a difficult problem. That's problem number 13. It gets more and more difficult as the time goes along. Well, not quite. I think we've finished most of the really difficult problems, because I suspect that the next one is not that difficult, uh, well, provided. Well, actually, this is quite also difficult. Question 14. This is round three, you must remember. You know, you've got the top people competing in the whole country here to come out in the top 10. So they make sure the problems are quite challenging. And you'll notice that there's a lot of things that you have to know here, which you don't learn in grades 8 and 9. So so you need to have a lot of additional knowledge, like what I'm telling you now. That's why this is useful, because I'm teaching you some new things. Earlier on, I taught you how to count, you know, the problem which will involve uh, the numbers 1, 3, 5, 7, and so on. You had to count up to 60 and so on and so forth. I taught you how to count, and now we did some congruency. And we also did similar triangles. All these are not in the syllabus, but they are things that they test you on. Okay, let's go to question 14. There are some green and some white balls in a box. Without looking, J removes 2 balls from the box. Again, I changed the question here because it was the original question was I couldn't understand it properly. But now, what this means is that, you see, somebody called J, he removes 2 balls from a box, which is it's got a number of he's got green balls. He's also got, I think, white balls. Oh, white balls disappear completely. These are green, and he's got 2 types of balls, right? Now, what he does is he withdraws 2 without looking. Right? He removes 2 balls. You got green and white. We don't know how many of them. But without looking, he just takes 2 out from there. If they are different colors, regard this as a win. So if he had a W and a green, for instance, he says win. But if he had W and W, he says, oh, I lost, right? So He repeats this action a large number of times. He keeps taking a white ball and a green ball, and a white, or whatever. He takes, just take two balls and he records what he has got. Now, the question is, if three green balls and one white ball are used in the game, show that the probability of winning is the same as that of losing. In other words, if you take, if it was a large number of times, if you played, say, 60 times, you'll have approximately 30 which are of opposite colors, white and green, and 30 will be also of the same color. In other words, the probability of winning is the same as that of losing. Right? So how do you do that? So we have to ask ourselves, you withdrawing two balls from, now you got three green balls and one white ball. So this is what you got. You got, I'm going to call it G1, G2. Although they're all the same colors, they are different balls. Remember that, right? When he's putting his hand and taking out one, it'll have the same color, but it may be a different ball. So I'm going to distinguish between the balls. So you got, suppose you got that. Now he's taking out two of them. So let's write down all the possibilities. When he takes out two of them, he could take out a white ball, and then you'll have to have, once you take out the white ball, you can't, there's no more white. You can take out white and G1, white and G2, and white and G3. Could be any one of the three balls. Or you could take out G1 and G2. You could have taken out those two green balls, or you could have taken out G1 and G3. Right? Those are two different balls. Or you could have taken out G2 and G3. Those are only three possibilities. G1, G2, G1, G3, and G2. Right. Now, where does he win? If he take them of different colors, then he records a win. So this is a win, for a tick for winning, and these are losses. So you can see his chances of winning are the same as the chances of losing. Right? That's what he says. The probability of winning the game is the same as that of losing. The probability of winning is 3 out of 6, which is a half. And the probability means the successes over the total. And the probability of losing is also half. So you've got the same probability. Right? That's what probability means. The chances are the same. So it's 3 out of 6. And the other one is also 3 out of 6. All right. Okay, so that takes care of the first one. The second one, if 9 balls are used in the game, show that the probability of winning is the same as that of, oh no. J still has an equal probability of winning. Right. Now he says even if 9 balls, you got equal probability, but how many balls must be green and how many balls must be white? Now that's a very interesting question. How do we solve that problem? Okay. So I'm going to take this thing out. Now this time I'm drawing 2 from 9. Now here's something which you must know in when you're doing round 3 junior. Here's a fact. The number of ways of choosing two objects from n objects is n into n minus 1 over 2. The number of ways of choosing two objects from n objects is n into n minus 1 over 2. Right. I'm just going to illustrate this. Suppose my objects will just give the name. We'll call it A, B, C, D, E. Right? Those are my objects. Right? I want to pick two objects. All right, let's do it. I'm going to call it, if I take two, I'll call it AB. Now, I can take AB. Earlier on, we said the way to do this is you take AB and then you take AC, and you can take AD, and you get AE. Only take all with A's in it. So that finishes all with A's in it. Now you start with B. You're not allowed to choose A anymore because we finished with A. You can go to BC, BC, BD, BE, right? So that finishes that. And then you can go to C. You have CD, CE, CD, CE, and then finally you have DE. Those are the only ways in which you can choose two objects from. Altogether, you got 10. You can see 4 plus 3 plus 2 plus 1. But I'm not going to say 10. I'm going to put 4 plus 3 plus 2 plus 1. So the number of ways of choosing two objects from 5 objects is 1 plus 2 plus 3 plus 4, not up to 5. Right? So in the same way, if you got n objects, the n of them, the number of ways of choosing two I'm going to write this backwards. 1 plus 2 plus 3 plus 4. It will be 1 plus 2 plus 3 all the way up to plus n minus 1, as we had 4 here. So if there are n objects, it's exactly the same method. You'll say, I started off with 4 here, you see, because I'm matching A with the others. So if there were n objects, I'm matching A with n minus 1. So I'll have to have n minus 1 in this column. And you're starting from 1 and you're going all the way. And this one here, you should know, right? Every person who's going to round 3 ought to know the formula for the 1 plus 2 plus 3 up to n. They will always ask this. 1 plus 2 plus 3 up to n is n into n plus 1 over n. So here you will have n minus 1 times n, or 2, I'm sorry, n into n plus 1 over 2. So here you have n minus 1 times n over 2. So that is the number of ways of choosing. There it is, n into n minus 1 over 2. Okay, so just remember that. Okay, I'm going to use this a couple of times. Now I got 9. They use in this game. J still has an equal probability of winning. Now I've got 9 altogether in this box. I don't know how many are green and how many are white. So we'll say let n be equal to the number of green balls, and therefore the number of white balls equals 9 minus n. See? To solve this problem, what I did was I actually took 2 green and 3 whites. I made it a little bit different from that one. I took 2 green and 2 white, and then I said, okay, let me work out all the, I'm calling it W1, W2, W3. I'm going to put these as subscripts, right? So you got the 2 green and 3 white. And I calculated what the probability is that you got of 2 different colors. So I did this now. I got to take W1. I can take W1G1, W1G2. Oh, let's take it like this, as we got it in this order here. Right, you got G1, G2, G1, W1, and as we did before, G1, W2, and G1, W3, right? G1, G2, G1, W1, right? So then I'll start with G2, G2, W1, G2, W2, G2, W3. And then I've got W1, W2, W1, W3, and W2, W3. Right. Now, let me just count the number of ways in which he loses. Right. Now, he loses, I'm going to put a tick for those. He loses here, he loses here, he loses here, because he's got 2 of the same colors. And he also loses here, he's got 2 of the same colors. But in all the other cases, he wins. So he loses 4 times out of 10 in this case. Right? Now how did he get 4? It's really 1 plus 3. This 3 is where you are choosing 2 W's from 3 W's. And this 1 is where you are choosing 2 G's from 2 G's. There's only one way in which you can choose 2 G's from 2 G's. And there are 3 ways in which you can choose 2 W's from 2 W's. So the number of ways, the chances of losing, number of ways of losing, right. Now you have to choose 2 green balls from N. Here I had N equals 2. Plus, here it's 2 green balls from 3. So again, it's 2 white from N 9 minus N, because there are N minus 1 white balls. So the total number of ways of losing, right, is where you choose 2 of the same color. Both are green or both are white. So I'm going to calculate the number of ways of losing. Then I can, from that, I'll be able to work out what the probability of winning is. Okay, so if now that I need to do a calculation here. To choose 2 from N, I just told you what it is. It's equal to N into N minus 1 over 2. And here, the number of ways of choosing 2 from 9 minus N, you would add it now, as we had 1 plus 3 before. Right? Now it's N is the number of balls, so it's 9 minus N. Here, the total number is 9 minus N. And the next one is 1 less than that, which is 8 minus N. Right? 2 from 9 minus N is 9 minus N times 1 less than that over 2. And then you can calculate this thing. And the half comes out, so you have N squared minus N. And you have to expand all this. You got 72 minus 17N plus n squared. When you take out the half, you get this. And then you got n squared plus n squared is 2n squared. And half of that is n squared. I'm taking out the half straight away. And you got minus 17 minus n minus 17n. Half it, you got minus 9n. Minus 18 divided by 2. And 72 divided by 2 is 36. Right. So this is the number of ways of losing. Now, you want this to be actually equal to, okay, the total number of ways of choosing 2 from 9. Remember, we had 3 over 6 before. So now we got the number of ways. We need to know what the total is. The number of ways, this is the number of ways of losing. So what is the total number of ways? And this time you have to check total number of ways is total is the number of ways of choosing 2 from 9. And that is 9 times 8 divided 9 times 8 divided by 2, and that is 36. That's the total number of ways. So the probability, if the probability is going to be a half, how many balls must be green? J still has the same equal probability of winning. So in other words, out of 36 different times of picking 2 from 9, right, you want equal probability. That means you want the number of ways of losing must be 18. The number of ways of losing must be 18. The number of ways of winning will be 18 also for equal probability. Now, when you work this out, you get n squared minus 9n plus 36 is 18. So you get n squared minus 9n plus 18 equals 0. 36 minus 18 goes there. And this, right, you do this in school, you factorize this a trinomial, n minus 3 into n minus 6, and you get n equals 3 or 6. N equals 3 or 6. Okay, in other words, the number of balls which must be in that, so n is the number of green, I think I said, yeah, n is the number of green. And so the number of green is either 3 or 6, right? In which case the number of white will be 6 or 3. So if your box has got only 3 green and 6 white, interesting that the number of ways of winning or losing is the same, right? You got an equal probability. If you run it 36 times, you'll get chances are that 18 of them will be green winning and 18 will be losing. Although you got a smaller number of green and a larger number of white. Okay, now that's the B part, and the C part I'm not going to do because this is taking too long. But try to do the C part on your own, and you will see that there is no solution. This is which can never be the same as a probability of losing. I can just give you a hint that what happens in part C is that in C, when you calculate the probability, the number of ways of winning over the total number, you will get an equation like this: n minus 1 equals 2n minus 1. No, no. Not sure exactly what you get, but you get a situation where you got 1 equals 0, which is impossible. See? Something like, I think 2n minus 2. Yeah. n minus 2n minus 2 is equal to n minus 1. Something like this. Yeah. Which is impossible. You can't have 2n minus 2 to be equal to 2n minus 1. Right? And then you'll say, if you know that the probability is the same, if you make that assumption, then you come to an impossibility. So you'll say, the way to work this thing out is they say it can never be the same. Then you say, assume that they are the same. It means the probability is a half. And when you start off with that, you come to an impossible situation. So therefore, the assumption that they are the same is false because you come to something which is impossible. All right. Okay. So that takes care of the number 14. And finally, number 15, which is a long haul. Okay, again, I'm going to just tell you what the problem is. You've got a black rook and a white rook, or you got two rooks. Two rooks. It doesn't matter what the colors are. Rooks is a castle. If you play chess, you know it looks like this piece. But you don't, even if you don't know how to play chess, what we are saying here in this problem is that this piece here, it can move anywhere along this line, anywhere on the vertical line or horizontal line. So if I got a rook here, for instance, I can move it anywhere to this point here, or anywhere to that point, anywhere, as long as there's no piece in between, right? You're not allowed to jump a piece, okay, or occupy a square in which another piece is resting. So you got an empty board here, and you got two rooks like this, and then A plays first. The idea now is when anyone is playing, if B is playing, he is not allowed to go across the column and the row in which A appears. So he can't cross this boundary here. See, A appears here. Likewise, he can't cross that boundary. So he is constrained to just be inside here, inside this, because A is occupying those boundaries. So now A plays first, and the question is now, what does he do in order to force a win? What must A play? That basically is the question, right? Now, when you think about it, for B not to have any moves whatsoever, because B can move that way or that way, he's got quite a lot of freedom. For B not to be able to move at all, he has to be stuck here in this corner, and A has to be here. Then B cannot move at all. If he can't move there, can't move there. In this situation here, A wins because B cannot move. So the idea is A must move in such a way that B is forced into this situation here, right? And so that is the question. What is the strategy that A must use in order to force a win? Interesting problem, right? And I'm telling you what the answer is. The answer is the following. All you have to do is A must move in such a way that A is in the same diagonal as B. So if A's first move, there's B here, A's first move will be here. So I called it, in this picture here, I called it A1, A's first move. So you can see, right? Now, B is going to take us the best move. He doesn't want to lose. So what does he do? He moves in such a way that he moves as further away from this corner as possible, right? So what he would do is, he can't move there because this is diagonal. He'll move up here. He'll try to move away, or he can even move here too, right? but in either case, it will be the same. He moves here, and then A now will move along the same diagonal where B is. So A will move here. So you can see B's first move is here, and A's first move, the second move is here, A2. And then B now, he wants to crawl his way here. Again, he just moves one square at a time, and A will just chase him all the way until he gets to the corner, right? So the A is here and B is here, right? So this is the largest number of moves that that can be taken for A to win. If A wants to, if B wants to commit suicide too soon, you just go right here and then go here, right? In the meantime, then A will just move up to that diagonal, and that diagonal, and he is there. All right, so B can, finish the game earlier, but if he extends it as far as possible, then what happens is he has to play the way I'm saying now. He has to keep away from this corner square. So the question is, what is the maximum number of moves that the game can last, assuming each player plays optimally, and A plays 7 times. I got A moves 7 times, yeah, and B moves 6 times. So therefore, the total number of moves will be 13. That's the maximum number. And the other ones, I don't know why they ask these questions, because if you know how to solve the first problem, the other ones are easy. Is there a winning strategy for player A? Yes, he moves along the same diagonal as B. Is there a winning strategy for player B? No, player B cannot win because he plays second. And as long as he plays second, A will push him into this. Which player can always force a win, and how can this be done? Same question. The person who plays second, the person who plays first wins. And how does he do it? He goes into the same diagonal as the other fellow. You see? So if B is here now, A goes there. If B is here, A goes there. He goes to the same diagonal as where B is, and he will constantly win. So that's the strategy. Okay, so that takes care of question 15, and also it brings us to the end of this long marathon session. Thank you very much for your attention, and enjoy the rest of the day.